Alright, picture this. You're going about your day, everything seems normal, right? But out there, in the vast expanse of the universe, there are things happening that defy everything we think we know. Cosmic phenomena that break the laws of physics as we understand them. These aren't just some sci-fi movie plot points. They're real, and they're happening right now. So, buckle up, because we're about to dive into the weird, the wild, and the downright mind-bending. You won't believe what's out there, and trust me, you won't want to miss this. Let's blast off. Our universe is full of mysteries that often challenge our understanding of physics. Some phenomena seem to break the laws we've come to rely on, leaving scientists scratching their heads. These aren't just minor glitches. They're significant events that appear to defy what we know about how the universe works. Take dark energy, for instance. It's the mysterious force causing the universe to expand at an accelerating rate. This goes against our expectations based on gravity, which should be slowing down the expansion. Dark energy acts like an invisible hand pushing everything apart. We don't know what it is, but we know it's there because we can see its effects. It's as if the universe is ignoring the rules of gravity we thought were set in stone. Then there are black holes. These cosmic beasts warp space and time to such an extreme that not even light can escape their grasp. At the center of a black hole, physics breaks down completely. Our equations predict a singularity, a point of infinite density where the laws of physics as we know them cease to exist. It's like the universe is saying, sorry, we don't make exceptions, but here's one. Quantum entanglement is another head-scratcher. Particles can become linked in such a way that changing one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance. It seems to violate the speed of light, which is supposed to be the ultimate speed limit. Yet, experiments confirm it happens. It's as if the universe has a secret shortcut we don't understand. These phenomena aren't just curiosities. They push us to rethink our understanding of reality. Each one is a puzzle piece that doesn't quite fit with the others. But that's the exciting part. Every time we encounter something that seems to break the rules, we have a chance to learn something new. The universe is full of surprises, and it's up to us to figure them out. The universe is expanding, and it's doing so at an accelerating rate. This might not sound too surprising, but it leads to some mind-bending consequences that seem to defy our everyday understanding of physics. One of the most fascinating is the illusion of faster-than-light motion. When we look at distant galaxies, we see that the ones farthest away are moving away from us at speeds that seem to exceed the speed of light. This isn't a violation of the laws of physics, though. It's a result of the very fabric of space itself stretching. Think of the universe as a vast, expanding loaf of raisin bread. As the dough rises, the raisins, which represent galaxies, move farther apart. If you're a raisin in the middle of the loaf, the raisins at the edges seem to be moving away from you faster than the ones nearby. In the cosmic bread, some raisins are so far away that their recession velocity appears to be faster than light. This isn't actual motion through space, but rather the expansion of space itself. It's a bit like watching 2 points on an inflating balloon move apart. They're not moving across the balloon's surface. The balloon is stretching between them. This phenomenon is often misunderstood. It doesn't mean that information or matter is traveling faster than light, which would indeed break the laws of physics. Instead, it's about the apparent speed at which distant objects move away from us due to the expansion of the universe. This expansion is governed by dark energy, a mysterious force that counteracts gravity and drives the acceleration. The farther away an object is, the more dominant this expansion becomes, leading to the illusion of faster-than-light speeds. The practical implications of this are profound. For one, it means that there's a cosmic horizon beyond which we can never see, no matter how powerful our telescopes become. Light from galaxies beyond this horizon will never reach us because the universe is expanding too quickly. This doesn't mean these galaxies are moving away at faster-than-light speeds in the traditional sense. It's more accurate to say that the space between us and them is stretching at a rate that outpaces the speed of light. It's a humbling reminder of the vast and mysterious nature of the cosmos. In the vast expanse of space, quantum scale effects challenge our classical understanding of physics. These phenomena occur at the tiniest scales, where particles behave in ways that seem counterintuitive. For instance, particles can exist in multiple places at once, a concept known as superposition. This isn't just a theoretical idea. It's been observed in experiments with particles like electrons and photons. In space, these effects can influence the behavior of matter and energy in ways that classical physics can't explain. Quantum entanglement is another mind-bending phenomenon. When two particles become entangled, their properties are linked, no matter how far apart they are. Changing one particle's state instantly affects the other, even if it's light years away. This spooky action at a distance, as Einstein called it, has been experimentally confirmed. In space, entanglement could play a role in the behavior of cosmic rays and other high-energy particles. Quantum tunneling is yet another example. In classical physics, particles need enough energy to overcome barriers. But in the quantum world, particles can sometimes tunnel through barriers they shouldn't be able to. This has been observed in laboratory settings and is thought to occur in space as well. For example, it might explain how protons fuse in the sun's core, a process that wouldn't happen under classical physics rules. These quantum scale effects aren't just theoretical curiosities. They have practical implications for our understanding of the universe. For example, quantum effects might influence the behavior of neutron stars and black holes. They could also play a role in the early universe's evolution, right after the Big Bang. By studying these phenomena, scientists hope to gain a deeper understanding of the fundamental laws governing our universe. Black holes are some of the most mysterious objects in the universe. They form when massive stars collapse under their own gravity, creating a point of infinite density known as a singularity. The area around a black hole, called the event horizon, is a boundary from which nothing, not even light, can escape. This is where things start to get really interesting, and also quite confusing. One of the biggest paradoxes is the information loss problem. According to the laws of physics, information about the state of a system should never be lost. For example, if you burn a piece of paper, the information on it might seem gone, but in reality, it's just been transformed into heat and light. However, when something falls into a black hole, it seems like the information about what that thing was is lost forever. This goes against a fundamental principle in physics called unitarity, which states that the total amount of information in the universe remains constant. Scientists are still trying to figure out what happens to this information. Some theories suggest that it might be encoded in the black hole's radiation, but this is still an open question. Another mind-bending aspect is the distortion of space-time. According to Einstein's theory of general relativity, massive objects like black holes warp the fabric of space-time. This means that time itself behaves differently near a black hole. If you were to watch someone fall into a black hole from a safe distance, you'd see them slow down and eventually freeze at the event horizon. From their perspective, though, they would fall right in. This is because time passes more slowly in stronger gravitational fields. It's like a cosmic traffic jam where time gets stuck. This distortion also leads to some strange effects, like time dilation, where time moves slower for objects in stronger gravitational fields. It's a trip to think about, but it's all part of what makes black holes so fascinating. Dark matter is a mysterious and invisible substance that doesn't emit, absorb, or reflect light, making it undetectable by conventional means. Yet, its presence is inferred through its gravitational effects on visible matter, like stars and galaxies. Scientists estimate that dark matter makes up about 27% of the universe's total mass and energy content. Its existence is crucial for explaining the observed gravitational effects that cannot be accounted for by the visible matter alone. One of the most intriguing aspects of dark matter is its role in altering gravity. In many galaxies, the visible matter we can see doesn't have enough gravitational pull to keep the galaxy from flying apart as it spins. This discrepancy suggests that there's an invisible mass exerting additional gravitational force. For instance, the way stars move within galaxies often doesn't match what we'd expect based on the visible matter alone. This anomaly implies that something else, dark matter, is contributing to the overall gravity. The distribution of dark matter isn't uniform. It forms a sort of invisible scaffold that shapes the large-scale structure of the universe. This scaffold influences the formation and evolution of galaxies. For example, in galaxy clusters, dark matter acts as a gravitational glue, holding together hundreds or even thousands of galaxies. Without dark matter, these clusters would likely dissipate over time due to the lack of sufficient gravitational force from the visible matter alone. Despite its pervasive influence, dark matter remains one of the biggest mysteries in modern astrophysics. Scientists are actively searching for ways to detect it directly. Various experiments are underway, using underground detectors, particle accelerators, and even space-based observatories. The goal is to understand what dark matter is made of and how it interacts with ordinary matter. Until then, its gravitational effects continue to provide crucial clues about the hidden architecture of our universe. In the vast expanse of the universe, there are phenomena that challenge our understanding of physics, particularly when it comes to energy. Some observations exceed the theoretical limits we've established, leaving scientists baffled and intrigued. One such puzzle is the concept of impossible energy emissions from certain cosmic objects. For instance, some blazars, which are active galactic nuclei, emit gamma rays with energies that seem to defy our current understanding of particle acceleration. These emissions are so powerful that they challenge the theoretical limits set by the synchrotron process, which is the mechanism we typically use to explain such high-energy emissions. Another intriguing case is the cosmic microwave background, CMB, radiation. This is the afterglow of the Big Bang, and it's incredibly uniform across the sky. However, there are slight fluctuations in this radiation, and some of these fluctuations seem to be larger than what our current theories can explain. These anomalies suggest that there might be something missing in our understanding of the early universe and its energy distribution. It's like finding a piece of a puzzle that doesn't quite fit with the rest, hinting that there might be a larger picture we haven't seen yet. Then there's the mystery of ultra-high-energy cosmic rays. These particles hit Earth's atmosphere with energies so high that it's hard to fathom their origins. According to our current theories, there shouldn't be particles with such high energies in the universe. Yet, they're detected regularly, and their sources remain unknown. It's as if the universe is playing a game of cosmic whack-a-mole, with these high-energy particles popping up where we least expect them. These energy inconsistencies aren't just interesting for their own sake. They push us to rethink our understanding of the universe and its underlying laws. Each inconsistency is a clue, a hint that there's more to the story than we currently know. It's like being a detective in a cosmic mystery, where each new piece of evidence challenges our preconceived notions and forces us to look at the case in a new light. And as we gather more data and refine our theories, we inch closer to unraveling these enigmas. In the vast expanse of the cosmos, there are phenomena that challenge our current understanding of physics. These are areas where our models and theories fail to fully explain the data we observe. One such area is the nature of dark matter and dark energy. We know they exist because of their gravitational effects on visible matter, but we can't directly observe them. This discrepancy leaves a lot of room for debate and speculation. Scientists have proposed various theories to explain these mysterious components of the universe, but none have been definitively proven. Another intriguing debate zone is the behavior of black holes. According to general relativity, nothing, not even light, can escape a black hole's event horizon. However, quantum mechanics suggests that information can't be destroyed, leading to the famous black hole information paradox. This contradiction between two fundamental theories has sparked intense debate. Some physicists propose that black holes might have a hair or that they could be portals to other universes, but these ideas are still speculative. Quantum entanglement also falls into this category. When two particles become entangled, their properties are linked regardless of the distance between them. This phenomenon, which Einstein famously referred to as spooky action at a distance, defies classical notions of locality and causality. While entanglement has been experimentally verified, its implications for our understanding of the universe are still not fully understood. Some interpretations, like the many-worlds interpretation, suggest that every quantum measurement creates a branching of the universe, but this is far from being a consensus. These debate zones highlight the boundaries of our current knowledge. They are not just gaps in our understanding but active areas of research and debate. Each phenomenon presents a puzzle that, when solved, could potentially revolutionize our understanding of the universe. Until then, they remain fascinating topics that challenge our intellect and spark our curiosity. The journey to unravel these mysteries is ongoing, and each new discovery brings us one step closer to a more comprehensive understanding of the cosmos. The discovery of cosmic phenomena that defy our current understanding of physics has sent ripples through the scientific community. These anomalies challenge the very foundations of our physical laws, hinting at a deeper, more complex reality. For instance, dark matter and dark energy make up about 95% of the universe, yet we can't directly observe them. They don't emit, absorb, or reflect light, making them invisible to our telescopes. This invisibility forces us to rely on indirect evidence, like the gravitational effects they have on visible matter. Such observations suggest that our current laws of physics might be incomplete. Consider the concept of dark energy, which is thought to be responsible for the accelerated expansion of the universe. It behaves in a way that contradicts our understanding of gravity and the behavior of matter. According to Einstein's theory of general relativity, gravity should slow down the expansion of the universe. However, Observations of distant supernovae show that the expansion is actually speeding up. This discrepancy suggests that our current theories might need a significant overhaul to accommodate this new understanding. Quantum entanglement is another phenomenon that bends the rules of classical physics. When two particles become entangled, their properties become interconnected, no matter the distance between them. Changing the state of one particle instantly affects the state of the other, seemingly violating the speed of light. This spooky action at a distance, as Einstein called it, challenges our notions of locality and causality. It suggests that our understanding of space and time might be more interconnected and complex than we previously thought. These cosmic anomalies push the boundaries of our knowledge, demanding a re-evaluation of our physical laws. Scientists are exploring new theories and models to explain these phenomena. Some are looking into modifications of general relativity, while others are delving into quantum field theories. The goal is to find a unified framework that can explain both the macroscopic world of galaxies and the microscopic world of particles. This quest for a theory of everything could lead to a complete rewrite of our physical laws, opening up new avenues for exploration and discovery. As we wrap up our journey through these mind-bending cosmic phenomena, let's recap the incredible things we've explored. We've seen black holes, those mysterious cosmic vacuum cleaners that warp space and time. We've marveled at dark matter, the invisible glue holding galaxies together. And we've pondered the enigmatic dark energy, the strange force speeding up the universe's expansion. These phenomena challenge our understanding of physics, pushing the boundaries of what we know and what we can imagine. It's mind-blowing to think that our universe is full of such puzzles, isn't it? These cosmic mysteries remind us that there's so much more to explore and understand. They inspire us to keep asking questions, to keep looking up at the night sky with wonder and curiosity. So, what's next? Well, the universe is vast and full of surprises. There are countless more phenomena out there waiting to be discovered and understood. Maybe you'll be the one to unravel the next cosmic mystery. If you enjoyed this video, don't forget to like, share, and subscribe for more mind-blowing content. And if you have any ideas for future videos, let us know in the comments. Let's continue this journey of discovery together. Until next time, keep looking up and keep wondering. The universe is waiting.